So in this problem we have a jib of total mass big M and length d that is attached to a vertical tower that is firmly planted in the ground. The crane load mass is going to be attached to the long end of the jib, and the counterweight of mass 5/3 big M is going to be attached to the short end of the jib. Now in part A of the problem we're asked to figure out what the maximum load mass is going to be if each cable can support a maximum tension of big mg. So the maximum tension in our cables is going to be big mg. Now we're going to analyze the torques about the pivot point, which is where the jib connects with the vertical tower. So at its maximum load capacity, the jib is going to experience a large torque by the right-hand rule into the page, which means that cable 2, which is supporting the load mass, is going to be supplying its maximum tension force, big mg. Now, cable 1 is just there to prevent the counterweight from falling, but the torque from the load mass is more than sufficient to keep the counterweight from falling, which means that cable 1 is just going to be slack. So cable 1 is not going to contribute any significant amount of torque to the system. So if we sum up the torques on the jib, we get that sum of torques is going to be, well, from the load mass, we're going to have mlg times this distance from the pivot point, which is 3/4 d, and we're taking the into the page to be the positive direction for torque. And then the force of gravity on the center of mass on the jib is also going to be a supply of torque that's going to be into the page, so it's positive. So that's going to be big M times G times the distance of a center of mass from the pivot point. So by symmetry, we're going to have that the center of mass is going to be a distance d/4 to the right of the pivot point. Now, the counterweight is going to supply a torque out of the page, so it's negative. And it's going to be given by 5/3 big M G times d/4. Now, to figure out the torque that cable 2 provides, we're going to have to figure out what the vertical component of the tension force is. So notice here that this is a 45, 45, 90 degree triangle, which means that this length is going to be the same as this length. So this side is d/4 and this side is d/3. So by Pythagorean theorem, the hypotenuse is going to be 5/12 times d. So the vertical component of the tension force of cable 2 is going to be d/4 over 5d/12, which is going to simplify to 3/5. So we have that torque from cable 2 is 3/5 big M times G times d/3. Now we're trying to figure out the maximum load such that the jib is at equilibrium, which means that the net torque is going to be 0. Alright, so if you isolate for the load mass and cancel out the factors of GD, we're going to get that 3/4 times ml is equal to big M times 5/3 times 1/4 is going to give us 5/12 plus a factor of 1/5 minus a factor of 1/4. that's just going to be big M times, well, let's put this over 60. So we get 25 plus 12 minus 15 all over 60, which is just going to equal, so 37 minus 15 is 22. 22 over 60 times big M. So this means that ML, the maximum load mass, is going to be given by 4/3 times 22 over 60 big M, which is going to simplify to 22 over 45 times big M. All right. So in part B of the problem, we have our crane system at rest with no load mass. Cable 1 and cable 2 then suddenly snap, causing the jib to rotate, and we're asked to find the speed of the counterweight right before it hits the vertical tower. So notice that the torque provided by the counterweight is greater in magnitude than the torque provided by the weight of the jib, which means that counterweight is going to fall. So here we've drawn a diagram of counterweight falling, and right before it hits the vertical tower. So here we see that the counterweight is now a distance d over 4 below the pivot point, and the center of mass of the jib is a distance d over 4 above the pivot point. So since the jib, or the bearing, rotates without friction, this means that the energy of our jib counterweight system is conserved. So our initial energy of our system is going to be equal to the final energy of our system. Now if we define the gravitational potential energy to be 0 at the level of the jib initially, then our initial energy of the system is just 0 because the counterweight and the jib are initially at rest, and we've defined their gravitational potential energy to be 0. So that's going to be equal to the potential energy plus the kinetic energy of the system right before the counterweight hits the vertical tower. So here we have that the potential energy, if we take the positive direction to be upwards, is going to be 5 over 3 times big M times G times d over 4. And that's going to be negative because it's a distance d over 4 below the pivot point. And we plus the potential energy of the jib, which is big M times G times d over 4, and it's positive since the center of mass is a distance d over 4 above the pivot point. So now we just have to account for the kinetic energy, which is 1/2 times its moment of inertia times its angular velocity squared. So for the jib, the moment of inertia, we're going to use a parallel axis theorem. So for a uniform rod of mass big M and length d, its moment of inertia when rotated about its endpoint is 1/12 big M d squared. Now the pivot point is a distance d over 4 upwards from the endpoint, which means that we have to add big M times d over 4 all squared. And that's all multiplied by omega squared to get our kinetic energy for the jib. So our kinetic energy for the counterweight is going to be 1/2 times its moment of inertia squared, or its moment of inertia, which is 5 over 3 times big M times D squared. Sorry, not D squared. D over 4 squared, all multiplied by omega squared. So if we isolate for omega, we get that big M times G times D over 6 is equal to omega squared over 2 times big M times D squared, all multiplied by 1/12 plus 1/8 times 1 over 16. Sorry, this should be 8 over 5 times 1 over 16. Or 8 over 3. There you go. And that simplifies to omega squared times M times D squared all over 8. So omega squared is 8 big M GD over 6 big M D squared, which gives us 4G over 3D, which means that omega is equal to 2 times the square root of G over 3D. So now we know what the angular velocity of the counterweight is right before it hits the vertical tower, which means that its speed is given by omega times its distance from the pivot point, which is d over 4. So that's equal to d over 4 times 2 times the square root of g over 3d, which gives us our final answer of 1/2 times the square root of g d over 3.